So our next and final speaker of this session this morning is Chip Shearer, who is going to be giving you an update on ANGSA. I know from my perspective, as Chip walks up, I had talked with Chip for probably about 10 years with him wanting to take a look at these Apollo samples, and thank goodness we're finally doing it, right? And this is another one where I'm trying to have a big tent and include other people. And so Chip regularly participates in our survey ECs, something that I'm really grateful for.
That was great. Thanks. As I mentioned yesterday, the ANGSA initiative was really designed to mimic a sample return mission from the moon. As such, it's really been extremely useful in utilizing and applying relatively new technologies that weren't available during Apollo, and test these new technologies in curation and sample preparation and preliminary examination that can be used for Artemis. In addition, the teams for ANGSA are multi-generational and international, and therefore it allows the Apollo generation of scientists and engineers to really interact in a dynamic environment with those early career people who will be important in Artemis. In addition, what this allows us to do is to take both aspects of this and allow early career people to be involved in preliminary examination of real lunar samples that nobody has seen before, and therefore, again, provide them with the taste and flavor of what could be happening in 4, 5, 6 years with Artemis. For those of you who aren't familiar with regards to ANGSA, it's really there are certain sample targets that we used, and most of these sample targets were either curated or prepared or stored in unique ways and they haven't been, in many cases, examined before by the scientific community. These include unopened vacuum sealed Apollo samples, and these were samples that were sealed on the surface of the moon. And the one we're using right now is 73001. This is part of a double drive tube, the lower part of that drive tube that was hammered in by Apollo astronauts at Station 3 in a landslide deposit off the South Massif. And that was a sample that we opened very recently. Also, the upper part of that double drive tube remained unopened in a unsealed drive tube, and that was 73002. And then we also had a series of frozen samples that had been frozen since I think December 1972, perhaps January 1973. So they were essentially frozen for almost 50 years before this team had a crack at them. These samples, again, were processed and curated in 2 different ways. The core samples were processed in a nitrogen glove box where they had actually been stored since they were returned. And the 4 slides to your left just shows the glove box we have used and some of the individuals involved in the processing of the samples. And then on the right, JSC developed a temporary cold curation facility and curated some of the frozen samples that people then received and have been working on. What I'd like to do is just illustrate again, just give you some highlights of some of the things that ANGSA has been doing and some of the results. What we've done recently is opened this sample 73001, which is part of this core sample vacuum container. And just to illustrate what's involved, the diagram to the upper left are examples of double drive tubes. These are hammered into the lunar surface, and the samples in these were placed into the image that's in the middle upper portion, a core sample vacuum container, and sealed on the surface of the moon. Once they were returned, they were placed into the container that's in the lower left part of the diagram. And this was an outer vacuum container. And then this outer vacuum container was stored for almost 50 years within a nitrogen glove box. What we were developing with our partners, our scientists and engineers, as a useful way of opening this container up and sampling the gas within it. And this was a two-step process. And one step was developing these tools because the Apollo program did not develop any of these. And the second was actually carrying out the gas extraction. And we had two partners that did most of the heavy lifting. Washington University, St. Louis produced the gas extraction, gas manifold, if you will, tool, which you can see is in the diagram on the far right. And this essentially collected the gas and stored the gas for future analyses. And what you're seeing there is an image of gas being collected from the outer vacuum container. And then ESA, in partnership with ANGSA, developed a core sample vacuum container piercing tool, which we utilize to pierce the core or the core sample vacuum container, store the gas, and then that was extracted by, again, the manifold. And we do have some results. Some of the sample was initially sent to Zach Sharp, who's a stable isotope geochemist at the University of New Mexico, and he did analyses on his series of mass spectrometers, primarily focusing upon major gas species and also nitrogen isotopes. And then a subsample of the gas were also sent to Washington University, where they were analyzed preliminarily for the noble gases. And there appears that this tool, our tools, and the container were somewhat successful, considering it's been sitting there for 50 years. There appears to be a non-atmospheric component in the core sample vacuum container sample, which is probably lunar in origin. Then there is also an atmospheric sample of unknown origin thus far, but it's not from the crew cabin, so there was not any leaking on returning the sample. There was no terrestrial atmosphere contamination. So at least at this stage, the most likely interpretation is that this gas is probably from the nitrogen glove box. And all these gas samples, or all these 2 gas samples, will be available shortly to the planetary science community to really carry out future studies. In addition, once the gas was extracted, these samples, or this core sample, was analyzed by XCT, X-ray computed tomography. And this just is a really quick cartoon, but it's really, really cool. And this is essentially moving down the core that you see to your left, and the images and cartoons that we're taking, or video that we're taking, so you can really see the distribution of lithic fragments, the size distribution. All of these data were really important for developing a strategy for curation. An analysis of grain size will allow us to do a detailed modeling of the dynamics of lunar landslides. And it also allows us to identify new lithologies that I'll be discussing shortly. In addition, using new technologies such as XCT imaging, we also had the University of Hawaii team come out and do multispectral analysis, which they discussed yesterday. And the diagram the middle diagram just illustrates some of the multispectral data from 73002. And this suggests that there seems to be a reddening of the regolith to the top, as you can see here. And this is linked to maturity. And we've to calculate maturities of these, and the I sub S FEO, for example, of the upper part is very mature on the order of 60 to 70, and most of the rest of the core, which is green in the middle diagram, is primarily immature on the order of I sub S FEO 10 to 20. They also did initial analyses of the much longer core 73001 and found that it was generally fairly homogeneous with regards to maturity, but they did note that there was some increase in maturity near the base of this core, which is rather puzzling. And one interpretation could be that during this landslide deposit, it scooped up some of the material from the previous landslide and incorporated it into the deposit. So we could potentially be close to the base of this landslide if that's the proper interpretation. My group received our 73001 samples like a week and a half ago or so, and we started sieving these and looking at the 150 to 250 micron size fraction that you can see to the far right by one of our students, Michael Cato. We really didn't see a change in the agglutinate population. So again, it's kind of odd what this observation means with regards to the multispectral analysis. However, what Michael did, he did find what appeared to be his interpretation were maybe some rounded agglutinates, because they're very fragile. And we won't really know until we have thin sections. They could be mistaken for small rounded impact melt breccias. In addition, some work by Steve Simon on 73002 illustrated some of the modal petrology of this size fraction, the 250 to 150 size fraction. And this just kind of illustrates on the diagram to your right, the variation in mineralogy. And as you would assume, the agglutinate percentage decreases from the top where it's fairly mature to the bottom, and in some cases totally disappearing. The Mari basalts that make up the floor of the Taurus Littoral Valley seems to be fairly low in abundance. We primarily have impact melt breccias and regolith breccias and some highland rocks, again suggesting that these may be representative of the South Massif. In addition, our team members from the University of Manchester did a wide range of analyses using SEM microprobe analyses to look at a continuous thin section of the core. The photographs, reflected light photographs, are the upper two diagrams of two of the thin sections, and the bottom two diagrams are some of their really very precise SEM imaging with extremely high resolution. And this allowed us to identify a variety of other very new samples that, again, were not defined in the larger samples that were collected in the Taurus Littoral Valley. So this is a great tool that will be available for Artemis and looking at core samples of this sort. Finally, something that's really, really cool that we found, and this was referred to yesterday, and I think the JSC curation people referred to this as alien poop, but they noticed in that little square area in the core, there's a lithic fragment that's in there. We didn't know what it was. The University of Hawaii group did some imaging and looked at the spectra of that class. And it seemed like the spectra matched some of the black glass. So this is perhaps a big chunk, a reasonably big chunk of volcanic glass that hasn't been identified or examined before. And then again, this is really, the next one I'm going to show you is just really cool. And I really haven't seen it on the big screen. So I'm going to press the button and back off from this, from the here to take a look at this.
1 minute. Chip.
Okay, great. This is the next to the last slide. And here we go. And this is again an XCT movie of this volcanic glass clod, very similar to the Apollo 15 glass clods. And what you can see along the edges up there are just amazing clods of volcanic glasses. And again, these are probably pyroclastic glasses that are a product of fire fountain in the surface of the moon and transport of molecules from the lunar interior to the surface. So this provides us with, again, a great new view of pyroclastic glasses and pyroclastic deposits. And then finally, to finish up on time, again, as I showed my last talk yesterday, I just really, again, wanted to invite you all to our celebration of the 50th anniversary of Apollo 17. And you can do this in two ways. One, come to the Apollo 17 ANGSA workshop that is at the LPI at the end of October. And this isn't just to tie to ANGSA participants, but for the whole lunar community, particularly those interested in Apollo 17. And there will be student and early career travel grants. And again, we also have a special session at AGU. Thank you. This has been really fun. No problem.
Thanks, Chip. That was an amazing movie to end things on. Wow. Wow.